General Physics 1. And now, here's your professor, Veranga Pereira.
Hello everyone, welcome back. We have started talking about rotation and specifically thinking about torque and Newton's second law for rotation. And we'll continue doing that. We'll talk about rotation for a couple of days now and talk about various aspects of it. Before we do that, let's take a look at this animation just to get us thinking about different kinds of circular motion you might encounter. As I said earlier in the class, when you are learning new concepts in physics, always think about where do you see this in the everyday life. When you think about rotation, what do you experience, right, on a day-to-day basis? So think about that. Here is an example of circular motion. The moon going around the Earth is roughly circular, right? It's not precisely a circle, but it's pretty close to a circle. And you can kind of see how the moon orbits the Earth, right? So we'll talk about this motion. We'll talk about the specific kind of acceleration that the moon is experiencing at this moment as it goes through this rotation. So our goals for today, we want to think about centripetal acceleration. Acceleration is a general concept. You now know what that is, but now we're giving specific names to certain accelerations, certain forces, things like that, right? So centripetal acceleration will lead us to a discussion about a centripetal force, right? Again, using Newton's second law, as you can see, a very important idea, right? We keep applying Newton's second law for various different cases, right? So if you have a linear motion, if you have rotation, this big idea still applies. When you have some sort of external effect, right? So whether it be a force or a torque, it causes momentum to change over time, right? That's Newton's second law very, very generally. Okay, so where we left off last time was with an instapole. And let's pick that back up before we carry on forward. And so if you answered that previously, don't worry about it. I just shifted it over. Or if you didn't answer it last time, not a problem. We'll just take the answer for this time. So if you have your notes from last class, you can pull that out. Keep working on this problem, right? So you've had a little bit of time to think about this. So let's take a minute and remind yourself of this problem. Maybe pull up your notes from last time where you were working on this, and we'll come back. Okay, so hopefully you had a chance to look at this. Let's go to the doc cam here and draw this out, right? So here's our diagram. Make sure you're drawing a diagram like this, right? It doesn't have to be exactly like I have it here, as long as you're marking down the essentials of the problem, then you're fine, right? So it doesn't have to be, as we've talked about, it doesn't have to be very artistic. Just capture the main ideas, right? Okay, so we have this. It's good to also think about a coordinate system, right? So here, let's stick to our conventional one, right? So x going to the right, y going up as positive. Okay, and that does mean positive z is coming at you, right? So remember, you can do the right-hand rule on the coordinate system itself. You can do x cross y essentially to get where positive z is. Your thumb will point in the direction of positive z. On a discussion at the very top, there is a thread that's pinned on additional resources, right? The video resources that's there. And I put in a video where I use Desmos to kind of help you practice the right-hand rule. So that's something you can watch yourself and then practice using that, right? So I just walked through how you set that up in Desmos, right? It's free. Desmos is free to use. So jump on there and watch that video just to get you a little bit hang of using the right-hand rule. So you want to be comfortable, as you'll see. It's not just something that appears in torque, and that's the only case you have to deal with it. It shows up in many different contexts in physics. So in this class, in the next class, right? If you're taking summer 2, the cross product is there, right? So it is to your advantage to make sure you understand it, right? Okay, so we're putting down all the information. We have the weight of the meter stick itself going through its center of mass, right? As we talked about, yes, the Earth is pulling on every single piece of the meter stick, right? But the sum effect, right, the net effect of all of that is to say, yes, that force goes right through the middle, right, the center of mass. And that's why the center of mass is important, because if you find out where the center of mass is, you can just put that's where the weight acts, right? Yet, even though, yes, of course, this little piece of the meter stick is being pulled down by the Earth, right? But there's a net effect of all the little piece of the meter stick being pulled down by the Earth. That net result is a force going through the center of mass, okay? All right, so here's our rotation point, the fulcrum, right? That's our rotation point. We have this additional mass that's hung from the zero end, right? So we'll call this the zero. I drew the coordinate system here just to be on the side, right? But if you want, you could draw it right here, right at the end, like right this point where x and y are right here. I think it just clutters up the diagram. But yeah, we're measuring from this end of the meter stick, right? Okay, so the meter stick is balanced, it says, right? Okay, so what do we apply here, right? So here's an application of the sum of the torques being 0, right? So we talked about for stability, right? If you have a static equilibrium, you have to have some of the forces being 0 and some of the torques being 0, right? So here, let's apply the sum of the torques to be 0, right? Okay, so when you do that, right, so sum of the torques must equal 0. Unlike forces, right, if you're just summing up the forces, all you have to do is pay attention to the directions, right? This is in the negative y direction, this is in the negative y direction, right? So that's what you have to pay attention to. And that's all it is, right? So you put it down on the equation. However, when you're talking about torque, you have to decide about which point are you going to calculate torque, and that's up to you to decide, okay? So you could pick this point as the point you're going to calculate torque about, okay? And if you did that, this particular force will not have a torque, right? Because it has no distance from the point you're considering, right? So it's not necessarily the physical rotation point. You're not limited to calculating the torque only about the physical rotation point. You're welcome to calculate torque about this point if you want, and you can, right? If you calculate the torque about this point, then what you have to do is calculate R, is that R, right? From your rotation, well, from your kind of torque calculation point, right? From that point, you're going to calculate torque. You can find your R to the force, that's this R. And then you also find this R to this force, right? From this point to this point is a certain distance, right? And then you'll have to do that, right? So, and then you'll also have to do the force that's acting here, right? That's pushing up, right? Because this meter stick is here on this fulcrum point, not only because of this force and this force, but there's another force pushing upward, right? There has to be, otherwise this thing will come straight down, right? So I'm not gonna, well, actually, let's just draw it so that you see that force there too. Let's use a different color here. There's another force here. Call it force up or something like that, right? There's another force, and that's where the sum of the forces being zero comes in, right? So negative force, add a positive force, they sum to zero. And that's why, in terms of a linear sense, it doesn't accelerate, right? So that's kind of, you have plenty of practice with doing some of the forces, so let's just focus on doing some of the torques, right? So let's pick a point to calculate torque, right? Now, what we are trying to find is the mass of the meter stick, right? So this is our unknown that we're trying to solve for, right? So we don't want to get rid of that variable, okay? We have some information about this force, right? It says it's an object, 0.5 kilograms. We have some information about this. This force is there, but nobody asked about it. Nobody cares about it, right? So it's something that we can kind of say, okay, can we get rid of it, right? And you can get rid of it and not be bothered in the torque calculation so long as you calculate torque about this point. Right? If you choose this point as your point for torque calculations, then that force itself won't come into this, right? Because it has no distance. That force has no distance from the point that you're trying to calculate torque, right? I don't want to say point of rotation because it's not that limited. Okay, so let's go one at a time. Let's pick this force, right? So this force here. How do I calculate torque? I need to find the distance, right? So from this point, I need to find the distance to the force, right? Going from here to here, that becomes my R, right? So I'm going to draw it very lightly because I don't want to draw too many things on the diagram. So that's R, right? So remember, torque R cross F, right? So you go from here to here, from the point you're trying to calculate torque, go from there to then locate your force, right? So you located your force, that's your vector R. So you do R cross F, the force, using your right-hand rule, positive and negative. Okay, so practice your right-hand rule. Make sure you're doing that on the screen, on your piece of paper, right? So you practice your right-hand rule. Either you do the curling method or you do the fixed finger method. Either way, whichever one you like, right? And let Jericho know in a discussion when you do R cross F, which way does the torque point, right? Does it point along the X direction, the Y direction, or we have Z, right? So Z is coming at you. That's the dot, right? So Z is coming at you, right? So which way is R cross F pointing for just this force, right? We're not going to do this one yet, just this force, because of the 0.5 kilogram object that's hung from the 0 point.
We're getting positive Z.
Positive Z, it's good, right? Positive Z is where it's going, right? Let's use the curling method, right? So 4 fingers along R, curl towards the force, right? The force pointing downward. So 4 fingers curl down, thumb points up towards you, right? Same direction as positive Z. So it becomes a positive number, okay? So this is equal to a positive number, right? R and F are perpendicular to each other, right? So the definition of torque, right, is R cross F. And the magnitude of torque is the magnitude of R times the magnitude of F sine of theta, right? So if these two vectors R and F are perpendicular to each other, sine of 90 degrees is 1, so it's just a multiplication, right? So in this case, we just have to multiply this distance, 25 centimeters, right, by this force. And this force is mass times g, right? So it's a 0.5 kilogram object. We know g, 9.8 meters per second squared, right? And that's it. That's torque due to this force. Okay, we'll do the other one now, right? So we've done that one. This force, right, this upward force due to this fulcrum doesn't come into play because we're calculating torque about this point. So there is no R, right? R is 0. So then if R is 0, this thing is 0. So this doesn't come into play. This does, right? Now this has a different R, right? It's not this R, right? So all you have to do is start from the point you're trying to calculate torque. Walk over, walk over, walk over, find that force. Okay, great, you found that force. That is now your R, right? Now you do R cross F. You use your right-hand rule again. And again, let Jericho know on ed discussion which way does torque point due to this force, right? The weight of the meter stick itself is now is a torque. It's a force, of course, but that force applying over a distance is a torque. Positive, negative, X, Y, or Z. Which way does it point?
We're getting a lot of answers for negative Z.
Okay, negative Z, good. So a lot of answers for negative Z is good. That means you're practicing your right-hand rule, getting the hang of it, right? So that's really good. R and the F, right? So 4 fingers along the direction of R, curl downwards towards the force. Your thumb is pointing inward, right? So when you're doing that, look at your right hand. Always use your right hand. Don't use your left hand, right? That's not how it works. It's a right-hand rule. So use your right hand. R cross F. Thumb is into the page is negative Z, right? So that means we put a negative number and we have to calculate the distance, right? So if you notice the center of mass of a meter stick is 100 centimeters. The center of mass of a meter stick is right in the middle, 50 centimeters. So you have this distance is 50 centimeters. We know this to be 25, so this must be 25 as well, right? So that becomes 25 centimeters, right? It is this distance that I'm trying to figure out. And then it has some mass. We don't know the mass of the meter stick, right? But we know G, right? So 9.8 meters per second squared still, right? So this plus this has to equal 0. So what does that mean about M? What must M be?
0.5.
Yeah, so it has to be 0.5. Kind of getting that? Okay, I'll wait a second to make sure to answer any questions that you have, right? So one of the big things here is this, right? So calculating torque, as you can see, there's a right-hand rule. You have to worry about, is it positive or negative? These things are really important. But one of the things that may kind of concern you or trip you up maybe is this arbitrariness of where you calculate torque about, okay? So you might say, well, what if I pick the wrong point? There isn't no wrong point here. It's out of convenience, right? So this condition, right? This condition must be true for this thing to not rotate and accelerate, okay? So that means this is true at this point. If you pick this point to be your point of your torque calculation, right? So that point, if this is it, this will apply. If you pick this point, this will apply. If you pick this random point right here, this will apply, right? So the only reason you pick one point or the other, well, okay, one of the reasons where you pick one point or the other is out of purely convenience and you want to do the problem as fast as you can, right? Imagine you pick this random point. Why would you do that, right? Because it would make your life harder, right? Because if you pick this point, it's not two forces that are causing torques, it's actually three forces that are causing torques, right? Because if you pick this point, this one will produce a torque about this point, this one will produce a torque about this point, and this one will produce a torque about this point. And when you do the sum of the torques, you have to list all three, right? And that means you have to solve for this. We don't know what this upward force is. Okay, you can kind of figure it out by looking at what's going on. But still, in a more complicated situation, maybe you'd have to spend some time thinking of what this upward force is when you really don't have to, right? So you'll get the hang of it when you do problems. It's just the choice of which point to pick to do torque calculations about is purely to make your life easier, right? It's kind of like rotating the coordinate system or not, right? So when we did an incline problem, for instance, right? So sometimes we rotate the coordinate system purely to make the problem-solving process faster, right? So you'll get more practice as you kind of go through it. You'll kind of get the hang of picking a certain point over another. Any questions about that?
We have quite a few questions on using the fixed right-hand rule, and they're wondering if you could go over it specifically for the right side.
This one?
Yeah.
Yeah. So let me back up here. Hopefully the studio folks are not going to get annoyed by me doing this. Okay. Let me back up. Hopefully that... Okay, so our fixed finger method, right? So it's always this, right? So in the case of a general cross product, right? So if I say sum vector, well, let's use a different color. If I say sum vector A crossed with sum vector B is equal to sum vector C, right? A and B are just some vector, right? Some mathematical thing. It's not specific. It's like saying variable X or variable Y or whatever it is, right? So these are just things. In physics, when we say torque is this, you don't have the option to say F cross R, right? It's always R cross F, okay? That's the definition of torque, right? So in kind of a mathematical sense, mathematically it doesn't care if you swap A and B. You can do A cross B, B cross A. You can do it, but it'll give you a different result for what C is. But in the case of the definition of torque, it's always R cross F. Remember that, right? So then when you're doing the right-hand rule, you start with the first vector. In this case, it's always R when you're talking about torque. So in the fixed finger method, your index finger, right? Your index finger is R. Okay, so you point your index finger in the direction of R. So from the point you're calculating torque, go along R, right? So that's your index finger. Your middle finger is your F, right? So the thing is, like with the fixed finger method, you can rotate your hand. So depending on the problem. So what you have to do here is kind of rotate your hand kind of like this, right? Because my index finger is going along R, and you'll notice my middle finger, right, is going along the force, and you can't see it. I'll kind of twist my arm, right? So there you are. So the thumb is pointing downward in this case, right? So if you did this, if you can see that, right? If you can see that, my thumb is pointing into the page in that case, so that's negative Z, right? So that's the fixed finger or the curly method, right? So 4 fingers along R, and then if I have 4 fingers along R, and then I curl my fingers downward, close my fist, then my thumb still points into the page, right? So fixed fingers, curly method, it doesn't matter, gives you the same result. Just find the one that you find most convenient for you, right? So I personally prefer doing this, right? I don't know why, it just feels easier for me to do. But if you think that the fixed finger method is easier for you, do that one, right? They're both the same thing, and they gives you the same result. You just have to pick one that works for you, right? Does that make sense? Okay, we'll zoom back in.
asking about applying a positive or negative direction for the radius. A student solved this problem saying that for the left side, they thought since the radius is going in a negative direction,
Yeah.
and then they still got the right answer because since the radius is going in the positive direction, they kind of applied their signs using that notation.
Yeah, so this is a very good question. So for one thing, yeah, you could think about, oh yeah, I'm gonna, since I'm taking the torque about this point, I'll consider this a negative distance and I'll consider this a positive distance. I would encourage you not to do that because it will probably throw off some sign somewhere and make it more confusing. What you want to think about is when you're thinking about torque, you have to apply the right-hand rule, right? And the positive or negative of torque comes from the right-hand rule because it depends on where your thumb is pointing, right? So is it into the page, out of the page? That's the direction of torque. So the big thing to take away is that torque, in this particular case, either in the positive z direction or the negative z direction, right? We're trying to determine where that is. So to do that, all you need to do is think about where the vector is pointing, right? This one goes to the left, this one goes down, right? Left and down, right? And then you apply the right-hand rule, you get the thumb pointing upward. That's how you determine the sign. I wouldn't really, I see what you're saying in terms of, yes, this is a negative distance from this point, but that'll just make it more confusing. So just treat it as a vector, it points in a certain direction, and that's all you need to care about when you're doing the torque calculation. Once you do that, once you know if it's positive or negative, then there are magnitudes, right? All I need is the magnitude of R, magnitude of F, and then sine if there's an angle between them. Okay? So just kind of do it that, I would recommend doing it that way, just kind of, if you're given, let's just kind of switch it up. Let's say you have an R like that, upward, and then you have a force like that. I'm just making up a new scenario here, right? And if you have this, don't think about, is this negative, right? Is the force negative? That's not important. When you're calculating torque, right, when you're saying, I want torque, which is equal to R cross F, right? It doesn't matter if this is going in the negative direction or whatever that is, right? What's important is this is going up and this is going to the left. And then I do the right-hand rule, R cross F, right? So R cross F, my thumb points up, right? And that means something depending on the coordinate system that you chose, right? So you want to have a coordinate system in mind, certainly, right? X goes this way, Y goes this way. You want to have that in mind. Think of that as the room in which you're working, right? Because the coordinate system is kind of the room where these vectors live, right? And so think of it that way. And so once you have the room set up and say, look, the room is oriented such a way, then you say, okay, R cross F, right-hand rule says it's up. Up means positive z, right? And that determines the sign of this. And once you have that, then they're just magnitudes. How long is R? 25 centimeters, okay. What's the magnitude of F, right? Then put that in. And then sine of whatever the angle is, right? And then that'll give you the magnitude, right? Do it that way. And I think it'll be more accurate that way instead of thinking about the direction of R being positive or negative before you even do the right-hand rule, right? Yeah, that's a good question. Other questions?
They were just wondering where the F sign, the sine theta came from. You did explain like when there are perpendicular, but they were just wondering where how do we know to use sine theta?
Oh, yeah, so sine theta comes from the definition of torque, right? And frankly, the definition of what a cross product is. Let's go back to the notes here. Yeah, so go back to when we talked about, so torque, right? This is how torque is defined. And we want to talk about what is a cross product. That's a cross product, right? A cross B. And we said we did some work on how to figure out what's the direction of c, some vector, right? If a and b are some arbitrary vectors, which way does c go? You have to use the right-hand rule, right? But the right-hand rule only tells you the direction of the result. So if you use r cross f, it'll tell you the direction of the torque, but it doesn't tell you the magnitude of torque. Right? So if you want to know how much torque is there, then that's a different equation, different setup, right? To do that is you have to use this. Let's put the papers together so it's not, there we go, right? So if you wanted to know the magnitude of the cross product, then it's the magnitude of A, magnitude of B, right? Meaning whatever the first two vectors were, right? So this is the first vector, this is the second vector, right? So whatever their magnitudes are, and there's a sign because it is quantifying how perpendicular these vectors are, right? If they're not perpendicular at all, if they're actually parallel to each other, then sign is set up to give you 0, okay? But if they're actually perpendicular and they're 90 degrees to each other, then sine of 90 degrees is 1, and you get the largest magnitude out of this thing, right? So the sign, right, is there essentially to quantify how perpendicular the two vectors are. For torque, right, let's say you're trying to take a bolt out of your car tire or something like that, right? The wheel of your car, you're trying to take the bolt off. You're trying to apply a torque. You want to apply the maximum torque. If you kind of try to do this, right, that won't work. That won't help you, right? So to produce the maximum torque, you want to be at 90 degrees, right? The distance and the force have to be 90 degrees to each other. That'll produce the maximum torque, right? So it has to do with how for one kind of in a mathematical sense how we define a cross product, but more in a physics sense how torque works, right? If you try to have a wrench like this, you want the distance to the force and the force itself to be perpendicular if you actually want to kind of minimize the effort you're putting, right? So if you want to get the maximum torque, make them perpendicular, because if you take a wrench like this and instead of pulling down like this, if you kind of pull that way on the wrench, you're not going to unscrew the bolt, right? Yeah, good question. Yeah, the cross product is new for almost every one of you, I'm sure, which is okay. You're kind of learning new things, but yeah, it's a generally speaking, it's a mathematical construct. We're taking that and applying into physics, right? Think about multiplication is a mathematical idea. It doesn't belong in physics, right, per se. Mathematically, it's a very broad idea of multiplying two numbers, right? It's not necessarily only for physics. You can use it for business or whatever, different topics, you can use multiplication. So a cross product is like that. It's not a physics thing, right? It's a general thing. It's a mathematical idea that exists in math. And we're borrowing it, taking it from math and saying, okay, that's very useful because that is what torque does. So we're going to use the idea of a cross product for torque, right? So we're borrowing from math here as a tool to kind of understand torque. Doing okay? Yeah. Cool. All right, so let's switch over to talk a little bit more about circular motion. And to set this up, let's take a look at this demo video, and then we'll talk about what's happening in the video when we come back. In this demo, we're going to look at circular motion. We have this tennis ball on a string, and so as I rotate this around, I'll try to maintain the same speed. Let's do that. Approximately the same speed. So now I can ask the question of, is this ball accelerating? And initially you might think, well, it's traveling at the same speed, so then no. But it is accelerating. As you can see, the ball is going in a circle. Velocity is a vector, so when the ball's here, the velocity may be pointed to in that direction, and as it goes around a circle, the velocity vector changes direction, and that is the definition of acceleration. So when the ball is going in a circle like this, it is accelerating. The velocity vector is changing direction as it goes around the circle. So as it's accelerating, there is a force pulling on the tennis ball, and that's produced by my hand. I'm trying to produce a force that tugs on the ball, making it go around in a circle. So circular motion with this tennis ball involves acceleration, specifically centripetal acceleration. And so this is a demo of circular motion. Okay, so let's go back to this idea of velocity, which we've been talking about, but really trying to think about the fact that it is a vector, it has a sense of direction, and it's really important in a case like the tennis ball and let's say the Earth going around the sun, right? So let's take an example, put a dot for the sun, and let's say that's the Earth going around. All right, so the Earth might kind of follow this path, more or less a circle. And at a moment in time, think about what's happening to the velocity, right? So let's freeze time for a second, right? Let's say your bird's eye view of the solar system, you leave the Earth, you go up and see what's going on, Earth going around the sun, and you'll notice at a moment the Earth has a velocity vector that of course changes with time, all right? And we have already defined what a velocity is, right? We've said the velocity is the derivative of position with respect to time. You already have this definition, right? So what's the position that changes with time? If you're talking about your car, right, you measure relative to your house, let's say, and you say, okay, I'm going to measure my car's position over time relative to my house, and okay, I can get a velocity because I know my position relative to the house is changing over time, right, as I travel. But in this case, with the Earth and the sun, the position vector goes from the sun to the Earth, right? So we're locating Earth with respect to the sun, right? So at any given point in time, the Earth is some position relative to the sun, and is of course changing, right? So when we say acceleration, we mean the change in velocity, right? So we say acceleration. Again, a vector, right? So as we get further and further along in physics, we have to treat these as they are, right? So we can't really just be wondering about the magnitude, right? We have to really consider, hey, these things have specific directions to think about, right? Okay, so same scenario. Let's think about, again, the sun and the Earth. If you watch the sun go around the Earth, right, takes about a year. To do this, right? So roughly 365 days. It's a little bit, not exactly, right? Thus the leap years and leap years and things like that. So, okay, so here's the sun, here's the Earth, and we have a velocity at one moment as the Earth gets over here, right? Let's say the Earth is here now after some time. Then the velocity vector of the Earth points like this now, right? At this point in time. If the Earth is here, okay, which way does the velocity vector point? This way, right? So what do we mean by acceleration in this case, right? Going back to the definition of acceleration, acceleration as a function of time, right, is defined to be the derivative of velocity with respect to time. Okay. Okay. What does that look like? So the acceleration that the Earth experiences, we're assuming this is a circle, right? Just to simplify, it's not exactly a circle, but let's assume it's approximately a circle. Then the velocity is this way, velocity is this way, velocity is this way. As the Earth goes around, right, the velocity vector changes. The direction of acceleration, right? We need to think about the direction of acceleration. Which way does acceleration point, right? And this is where alpha equals ma helps you out, right? So sum up all the forces. That's equal to mass times acceleration, right? Oops, should do that. Sum of the forces, right? So the direction of acceleration is in the direction of the net force, right? So in the case of just assuming we have the Earth and the Sun, ignore Jupiter, ignore all this other stars, right? Just kind of focus on the Earth and the Sun. Which way does the net force on the Earth go? Where's the force coming from?
It's coming from the sun.
Yeah, so there's the Sun, right? So the Earth, the net force on the Earth is from the Sun. So the net force is just the gravitational pull, right? So there's the force, let's call it net, right? So the net force is that way. And as a result of that, what does that tell you from this, right? From F equals ma, what does that say about acceleration? Which way is the acceleration? Towards the sun, right? So wherever the force is, right? The net force, that's the direction of the acceleration. Wherever the acceleration is, that's the direction of the net force. They have to go together, right? They're pointing in the same direction. So the acceleration, right? I'm going to draw it slightly offset because just to show it, is also towards the center, right? Towards the center of the circle, which is towards the sun. And that is your acceleration. Okay. And when you get over here, right, the Earth is over here, the acceleration is now, again, pointing towards the sun. That is your acceleration. When you're over here, again, pointing towards the sun. Now, this is different from you being in a car or a bicycle, right? Because when you're in a car, for instance, and you accelerate, let's say, from rest and you start going on the freeway or something like that, 65 miles an hour, then the velocity vector and acceleration vector are in the same direction. If you hit the brakes, they're in the opposite direction, right? But you haven't maybe thought about a case where the velocity vector and the acceleration vector are perpendicular to each other, right? They're 90 degrees in this case to each other, right? So that's still an acceleration, because what this acceleration is doing is making the velocity vector change in direction, right? So if you start with a velocity vector that points like this is your velocity, and you have an acceleration that points in this direction, the effect of this is to rotate the velocity vector, right? So it doesn't change the magnitude of the velocity vector, right? So just like in the case of the tennis ball, if you're swirling your tennis ball around, right? Or in the case of something going like the Earth going around around the sun in a circle, the magnitude of this velocity does not change, right? What's changing is the direction of velocity, right? So this velocity, when the velocity is pointing like this in this instance, and the acceleration is sideways like this, what it does is tries to yank it this way, right? So when the velocity vector is pointing like this and the acceleration is like this, it tends to kind of rotate it this way, right? So it's kind of like tugging it along and tugging it as it goes around, and that's what keeps the velocity vector changing direction the whole time, right? Does that make sense? So it is an acceleration, but be careful, right? Because when you kind of think of it before this class, when you thought about acceleration, you probably thought, okay, change in speed, right? Do I go faster or slower? But it's not, it's more than that. It's also are you changing directions? But you could be going 65 miles an hour and still accelerating. Right? If you're going in your car, you're going in circles at 65 miles an hour, you are accelerating. Right? And that's important because there's a little bit more detail hiding in here than it may appear at first. Right? At first, it might appear that, oh, all it's about is speeding up or slowing down. It's not. It's more than that. It is that, right? So you could have the velocity vector itself changing in magnitude. You could be going faster or slower, right? But it doesn't have to be that way. You could be going exactly at the same speed, 65 miles an hour. If you're going in a circle over and again, you're still accelerating. And that means you have a net force on you. This specific acceleration, right, is called centripetal acceleration. And the way you calculate that is you take the magnitude of velocity, right, the speed, square it, and you divide by the radius of your circle. Okay? It is a specific acceleration, right? In the case of circular motion, right, you're going around in a circle, then there's a particular kind of acceleration we're talking about. And centripetal means center seeking, right? So the acceleration points towards the center, right? Centripetal. There is another term you may have seen is centrifugal. Ignore that. There's a bit of an explanation of what that is, and that acceleration's there when you're in a reference frame that is also accelerating, right? So if you are in a car going around in a circle, your car itself is accelerating. Your reference frame, right? Your XY coordinate system itself is accelerating. And when that coordinate system is accelerating, F equals ma, you have to be a little careful because Newton's laws applies when this thing itself is not accelerating. Okay? So if you have a coordinate system, wherever you fix the coordinate system, that coordinate system should not accelerate for this to be precisely true. If the coordinate system is accelerating, right, in the case of you in a car going around in a circle really fast, right, that if your reference frame is your car, then that reference frame is accelerating, and then it produces these fictitious forces. It seems like there are these new forces that appear, but it's not. They're not new forces. They're not new accelerations. And then that fictitious, right, the seemingly acceleration that you feel is often called centrifugal acceleration. Ignore that because it'll make things more confusing. If you want to know what that is and kind of the details of it, look that up. But just be careful. The critical one you want to, like the actual one that's important and one you should be paying attention to is centripetal, meaning center seeking. That's a very real thing caused by a very real force. Okay? And so just kind of be aware there are two terms that are kind of in the I don't know, people talk about it. And so if you're seeing the other one, centrifugal, that's the fictitious one. There's a reason why that's appearing, and the reason for that is due to the coordinate system accelerating, right? And there's ways to deal with coordinate systems that are accelerating, and we can get into that later. But the central idea, right? So the key idea is centripetal acceleration, right? That's a very real thing, and it's really important that you know what it is, right? Questions about this, Sharko? Okay, so let's do an Insta poll that'll probably generate some questions, some thoughts. Let's switch over and send the Insta poll your way. Give it a second. There we go. All right, read through the question, make sure you're drawing a diagram, right? Don't skip that step. Spend about a minute and a half on this, ask questions on that discussion, and we'll be back. Let's see. Okay, good. Some have gotten their answer, and if you haven't, don't worry, just keep working on it. Double check that you have a diagram, right? So that's a good place to start to think. So you can think through the problem as you jot down some notes on your, and then kind of on your diagram, kind of helps you think through, right? So switching to the dockhand, let's draw a picture. We have a mass. Tell you is 10 kilograms. It's attached to a string. It breaks at a certain force value, right? So at a certain point, it'll break, which is realistic, right? So if you have a string and you fix any object and you try to swirl it around your head, you know it doesn't have infinite strength, right? At some point, things break, right? Okay, so how do we draw this, right? So in the case like this, that's the object. I would recommend maybe think about it in a kind of a bird's eye view, because what you want to do is see the rotational motion, right? So kind of visualize how this thing would go around in a circle. So here's our mass. It goes around in a circle kind of like this. Okay, so here's our circle. It's not quite circular, but close enough. You can draw a better circle than me. Okay, so here's our center point, right? So there is a force pulling on this. That's what keeps it going around in a circle. There has to be a force that way. Let's think about the kind of breaking point, right? So we want to figure out the maximum speed, right? That's your hint that let's just push this to its limit, right? The limit is it can get up to 1,500 newtons. Of course, it can be less, but then that means the speed is smaller, right? But let's push it to the limit, right? So we want to see when this string breaks. So we want to see, okay, if it applied 1,500 newtons of force, how fast would this thing be going? This is still F equals ma, right? So we're still applying. Notice that it's a very important idea because we keep applying it over and over and over again, right? It's really, really important. F equals ma. When you're thinking about the free body diagram for the 10 kilogram object, what are the forces acting on it, right? And for this, just imagine you're in deep space, right? You're not going to worry about gravity. If you don't want to, if that makes you uncomfortable and you're like, well, I want to include gravity, you can also think about this on a table that has no friction, right? Then it would be the same kind of effect where there's a force this way that makes it go around in a circle. And then, of course, there is gravity, but then there's also a normal force that cancels out, right? So then in the vertical direction, the two forces will cancel, and the net force, right, is still just the 1,500 newtons. There is an acceleration, right? So now when you're talking about circular motion, there's a specific acceleration you should be thinking about. So when you see A like this, you should already be thinking about substituting this for this, right? Because we have a specific acceleration that we are considering. We need a R. What's the R? So the R, they tell you, right, is 90 centimeters, okay? Centimeters are not standard units, right? So what I would do, recommend you do, is write down the number that they tell you as is, without doing any conversions, right? Because you can, if you're looking down on your notes or your scratch work during an exam, you can see 90. You can see 90 on the question prompt. Then the centimeters, you deal with it like this. You say, okay, 10 to the power of minus 2 meters. Right? I just converted centimeters to meters, right? Because I know centi, right, 100. So it's 100 centimeters to a meter, right? So that's how I would kind of write this down. As you get further along, that's how I do it. So, you know, I'm just kind of telling you what I'm doing. This probably will help you, right? That way you don't have to do a conversion and then list that conversion, which is different from what shows up in the problem, right? So now when I look at this and go, that's 90 centimeters, right? Listed as meters, of course. All right, so now solving for the speed, right? Velocity, magnitude of velocity squared, so the speed. What we want to do is solve for that first, right? So we have the force, let's say applied force is equal to the mass times velocity squared divided by r, right? Move the terms over, so we have the force applied times r divided by m, and then we take the square root to get the speed, right, magnitude of velocity. Plugging in the numbers, let's see, what are we getting? I'm going to switch over to the computer here. 12 looks like the popular answer, as you can see, right? So if you going back to the notes, if you put in the force, right, so 1500 newtons into the force, you put in the r value in here, you put the m, take the square root, don't forget the square root, right? That should give you 12 meters per second. That's as fast as you can go, because if you try to go any faster, it'll break the string. How are we doing questions-wise?
One student asked, I think they just solved it. They solved for acceleration first, but they asked if they could solve for acceleration using F equals ma and then plug that into the v squared over r, which I think
Yeah, I think so.
which is
Yeah,
another
yeah.
way of doing it.
Yeah, different ways to do this, right? The thing is, as long as you're following the physics, the math is up to you. Of course, obviously, do something mathematically valid, right? So, but the thing is that there are options that are available to you, right? There's a certain freedom of solving problems. So there are certain rules to follow, of course, right? You have to make sure the physics is right. You have to do things mathematically correctly. But even then, there is different ways that I might solve the problem versus Jericho, right, the other TAs. Everybody might solve this slightly differently, right? And that's okay, as long as you get the correct answer. So you want to do things that are kind of make sense to you, and then you can do it accurately, you can do it as fast as you can, right? These are the sorts of things. So there is a certain subjectivity to solving problems, right? There, how particularly you draw the diagram, and you know the kind of which or exact order of operations that you go through. That's somewhat up to you. Okay, let's try another Instapol. Continue doing some circular motion problems here. I'm gonna zoom in here. There are several options to choose from, right? So there's a question, and they're asking which of the following statements is or are true. So you have 3 statements to choose from. So on your device, you should see different options to choose from. So what I'm going to do is just zoom into the problem itself, right? Because the answer choices are going to show up on your device. So consider these 3 statements. Pick the one you think, or ones you think are correct. Let's take a minute and a half, put your answers in. As always, make sure you're putting answers into the Instapols, right? The mere fact of trying it out is tremendously helpful to your own learning. If you don't get it initially correct, that's fine, right? We're all learning. If I learn something new, right, for the first time, I'm going to make mistakes. But the mistakes are important because when you make the mistakes, you learn what it is. And as opposed to kind of being passive, right? If I'm just watching, right? If I'm watching somebody do a skill, I don't learn as much, right? So I have to actually go in and do the thing. So do it, and you can always change your answer, right? As you can see, we're coming together collectively as a class to the correct answer. So give it a shot, right? Take an attempt. Okay, let's take a minute and a half, and we'll come back. Okay, great. Let's see. Zoom out and see where we are. Okay, so most popular answer is none of the above. Then we have 2 only, which is the acceleration is constant, and then other choices as well. Okay, so let's take it one at a time and see what's going on, right? So the object moves at constant speed in a circular path. Let's pull my diagram from before, right? And let's switch to the notes. This could be this scenario, right? I'm using the Earth going around the sun. This could be a tennis ball on a string, right? So something going around in a circle, right? It's said that it's a constant speed, right? So we know that is not true, right? That statement, the velocity is constant, is not true, right? Because we talked about how the direction of velocity keeps changing, right? And that counts, right? Because if we're saying, is this thing changing? Well, if the direction of the position is changing, right, then this is changing, right? So velocity is changing even though you're going at a constant speed in a circular path, right? So it's not 1. Let's think about 2. The acceleration is constant, okay? Is the acceleration constant? Acceleration in itself is a vector, right? So if you look at the Earth, which direction is the acceleration pointing in this case? Up, down on the screen, left, right?
Left.
To the left. When you come up here, where is it pointing now?
Down right.
Down right, right? So the vector itself is changing direction. What does that mean about acceleration?
It's not constant.
Sorry?
It's not constant.
It's not. So what is constant is the magnitude, right? So the magnitude of acceleration is constant because that magnitude has to do with the force, right? The force between the Earth and the Sun is not changing if you're thinking about it in a circular path, right? So the mass of the Earth is not changing, the mass of the Sun is not changing, the distance between them is not changing, right? Again, in reality, I always keep giving caveats. The reality is the Earth's orbit is an ellipse, okay? It's a little squishy circle, but it's not that dramatically different from a circle, right? If you look at an actual accurate kind of animation, like go on NASA and pull up an accurate distance depiction of what the Earth's orbit looks like, it looks pretty close to a circle, right? And just look at it. So yes, we can kind of more or less approximate it as a circle, meaning that the distance is not changing, right? In reality, it's changing by a very, very small amount as the Earth goes around the Sun. But you can kind of approximate it as not changing. In that case, right, the force, the universal gravitational constant, big G, is not changing, right? The mass of the Sun is not changing. The Earth is not changing mass, right? The distance is nothing's changing in terms of the force. So the acceleration, right, is the same in terms of magnitude. However, notice that the acceleration vector points this way here, and then points this way over here, and then points this way over here. If a vector is changing direction, it's changing, right? Therefore, the acceleration here is not constant, right? The magnitude of acceleration is constant. So there's a subtle point there, right? So if you read number 2 as the magnitude of acceleration is constant, then that's true. But if we're talking about acceleration as a vector itself, then it's not true. It's not constant. Okay, subtle point, but it's important. Number 3, right? So switching over to the computer, the net force on the object is 0 since its speed is constant. Is that true? Right? We know there's a net force, right? Going to the notes here. We know there's a net force on the Earth, right? The Sun is there pulling on the Earth. And if there's a net force, there is an acceleration, right? And vice versa. If you know that there's a net force, there will be an acceleration. And if you know there's an acceleration, you can definitely say there is a net force. You can be very confident that that's true, right? So it's both ways. It applies both ways. Okay? So there is a net force. So the answer is what? Going to our computer. Gotta turn off and back there. Okay. None of the above are true, right? So none of the above are true here in this case. Good. So let's go to our notes and we'll consider kind of a practical example of circular motion. And what we're going to do is think about a car going on a ramp, okay? And if you've been on the freeway and you get on the freeway, off the freeway, certain segments of the exit ramp seem like a segment of a circle, right? So let's see if we have this problem. And I'm going to draw a piece of the road here. This is a piece of the road. Okay, that could be the exit ramp, on-ramp onto the freeway, right? So certain parts of the road are kind of curvy like this, right? Looking from the top-down view, from bird's eye view. And if you continue this on, it would be a circle, right? But it doesn't have to be a circle, right? So there's just a segment of the road that is essentially just some segment of a giant circle. So you can still have a radius of curvature, right, to this. This segment has a certain radius because it is essentially part of a giant circle. And what we want to do is consider a car that is traveling on this road, and the car itself has some velocity. Okay, that's the bird's eye view. If you're on one of these ramps, you'll probably notice that they're not flat, right? So next time, if you haven't noticed, next time, kind of when you're on these kind of circular roads, like segments of the road, not necessarily a straight road, right? Not just kind of a straight line of a freeway. That's not generally kind of tilted, but these segments of getting on and off freeways, particularly, are kind of not flat on the road, they're kind of tilted, right? So from a side view, let's say bird's eye view, let's say you come down, fly over here and look at from this direction, what does this look like? It looks like this, right? It seems like a ramp, and here's where the car is. Okay, so ask questions if the different views don't make sense, right? So one view is the bird's eye view on the left here, and then what I'm going to do is on the right show you kind of the more profile view, right? So if you are a bird and you're viewing this from up here, but then you fly down and kind of view from this angle here, what does this look like? This road looks tilted, right? It is not level with the ground, but it's got a certain angle like this. And we want to figure out why that is. That's on purpose. That's designed that way. And we're getting at kind of safety of driving on roads. We want to consider designing a road like this and think about what angle would you make this, right? And designing a road, you want to think about not just what kind of cars go on this road and how many, but also the conditions of the road, right? So particularly like in Texas, in the winter, right? Sometimes there are freezes, right, where there's the moisture that freezes on the ground, and that might reduce the friction to almost zero, maybe not precisely zero, but you might lose friction entirely. Right? So when you're designing a road, you want to be careful, thinking about, okay, what's the worst case scenario, right? There's ice on the road and there's a car traveling, right? Can it make this turn without any friction, right? If you made this road flat, right? It wasn't curved like this and it was just flat and the car was trying to go into the page, right? Kind of trying to go around the circle, it couldn't make the turn, right? Because without friction, there's nothing that makes it kind of go around in the circle. If you tried to go in this direction on a flat road without any friction, you just go straight in a straight line, right? There's nothing to apply a force that makes you go in a circle, right? No friction, object in motion stays in motion in a straight line, right? So you don't want to design this road to be flat. You want it to have this angle because the angle is going to help you go around the circle without any friction. Okay, so worst case scenario, and we'll see how that works, right? Because we will think about the forces involved, right? Okay, so let's take this car. We're going to put the coordinate system right through the middle of this car. We're not going to rotate the coordinate system. I'll talk about why that is in a second, but we're not going to rotate the coordinate system. It is to your advantage not to rotate the coordinate system this time. It's always about what is more advantageous to you to solve the problem. In the case of this problem, it is not to your advantage to rotate the coordinate system. You can still, if you want to. You have the coordinate system, put the forces, go ahead. I'm going to pause for a second while you do that, right? You always want to practice doing free body diagrams. On this car, what are the external forces acting on this car? Put them down on your notes. You're welcome to share on that discussion if you want to share. Jericho loves seeing it. So hopefully you're putting some forces on your free body diagram of the car, right? So one of the good ones to start with is the weight of the car, force due to gravity, right? That was a good one to start with. It's towards the center of the earth, right? That's where it points. We have a normal force, right? The surface of the road pushes perpendicular to it. We have a normal force. Okay, and there's no friction, right? So there's no friction. Well, they could be. We're just taking the worst case scenario where we assume there is no friction. We're not going to rely on friction to go around in this circle. No friction, right? So this normal force has an angle, right? Has the same angle as this angle. Okay. You can play that game with perpendicular lines here as well, right? So here's the line, that makes up this angle. Here's this line, and here's this line, that makes up that angle. This line here is perpendicular to this line. This line here is perpendicular to this line, right? And if you can identify that, you can say that this angle and this angle are the same. Right? It's just a fast way to get to the fact that, yeah, these two angles are the same, right? And on Ed discussion, under resources, I put in a PDF as more of a mathematical proof of these sort of identifications, right? A little bit more detailed. If you're not happy with the perpendicular lines argument, you get a more detailed explanation of why that is the case, right? Why the angles add up like this. So theta and theta, we have the forces, those are the only two forces. Now you know what you're supposed to do, right? So you're supposed to sum up forces in the x direction, right? So sum up all the forces in the x direction, list that. Sum up all the forces in the y direction, list those. You have to make a decision if F equals ma is ma on the right-hand side. Do the left-hand side first, right? Sum up all the forces first. And then we can think about, in each case, x and y, is ma, that a part, is it 0, is it some value? We have to decide, right? So go ahead and put the forces down on your notes first. Okay, so in the x direction, what do we have in the x direction? None of the weight is in the x direction. Sum of the normal forces in the x direction, right? So here's our hypotenuse of a right triangle. We are going to make ourselves a right triangle to help us break up this vector, right? So here's the right triangle. We're trying to find the x component of this, so this side of this right triangle is what we're after. it's the opposite side to the angle here, right? And notice that it's in the negative direction, right? So from the center of your coordinate system, how do you get to the end of the normal force vector? You have to go in the positive y direction and go in the negative x direction. So the x component will be negative normal force sine of theta, right? Y sine, because here's the angle, here's the opposite side we're trying to solve for, right? And that's the only force in the x direction. We set it equal to, we'll decide if it's MA or 0 in a second, right? So let's do the y components also. We need the y component of the normal force, right? So the positive normal force cosine of theta. And we need the weight, right? So it's a negative direction, so minus mg for the car, right? That's equal to the MA part, right? So going back to the x component, coming back here, is it MA, is it 0? Right, we had to decide. This car is accelerating, right? Because if it's going in a circle, for this segment of this road, it's going in a circle, it is accelerating, and the acceleration that it feels is towards the center of that road. The segment of the road is part of a circle. The acceleration's towards that center, right? So that acceleration's in the negative x direction. So there is an acceleration. So negative mass of the car, velocity squared divided by r. Right? So there is an MA part, right? F equals MA, because this car is accelerating, and it's accelerating that way. It has to be. If it wasn't accelerating that way, it wouldn't be going in a circle, right? And that's why you want both these views, right? Because you want the top-down bird's eye view, and you want the profile side view, because both are really necessary to see, because this is a dynamic thing where the car is going around a circle, and we're trying to draw a cartoon, right, in stages, and it makes it a little bit harder to visualize. So there's an acceleration, negative x direction, list that. In the y direction, right, so here's our y direction, is there acceleration or not? Well, we're assuming that the car stays put along this ramp. It's actually going along the ramp, but it's not levitating, it's not going into the ramp, right? It's not accelerating the y direction. Let's say it had a positive acceleration in the y direction, that would mean it would levitate off the road, right? Does that make sense? So it doesn't do that, right? So in the y direction, it doesn't do that. So then we can say there's no acceleration in the y. Okay, so we have two equations. Let me rewrite them. So let me switch to a different paper, rewrite them. So I'm going to copy them down here. This equation, the negatives will cancel. Then we'll have the normal force sine of theta is equal to, pen's fading, mv squared divided by r. Just copying that over. This one, I'm just going to move the mg to the other side. So I have n cosine of theta is equal to mg. Okay, I'm just transferring over. Now I'm going to use that trick that's really handy, is I'm going to divide one equation by another, and that just means on the left-hand side divide those terms, and the right-hand side divide those terms with each other. And when you do that, right, the normal force cancels, the mass cancels, right? There's a few terms left over, and we have a sine divided by a cosine that's tangent. Okay? So then what you're left with, you're saying that tangent of theta is equal to v squared divided by rg. Or you can now solve for it, because if you're designing the road, right? What you might be trying to determine is what is this angle, what should that be? So you can solve for the angle is equal to the arctangent of v squared divided by r times g. Okay. We have an angle, right? So for a particular speed, right, and a size of the road, right? So the r is the radius of curvature of this road, which you can design, right? You can set that as the person making the road. You can say, I'm going to give it a certain r value. G is g, right? So 9.8 meters per second, you're not changing that. That's just a number you have to use. R is something you can decide, right? You can make the road bigger, smaller, right? But importantly, notice there's a certain speed which this will work, right? At a certain speed for a certain road, you can not have friction at all and still go around the circle, which is quite impressive, right? Because imagine you're a car and I tell you, oh yeah, you're going to make this turn going at, I don't know, 40 miles an hour or something like that, and there's zero friction on the road, right? And you can still make this turn. No problem, right? Given a certain speed, you can still do this. So this is part of the reason why when you go on roads, particularly on exit ramps, on ramps, right, they tell you this is the safe speed to go off this ramp, because they're thinking about these things, right? If you go way too fast around this around a turn, your car cannot produce enough friction to make you go around and so you'll just end up on a wall somewhere, right? You'll go in a straight line, right? So these are some of the considerations when you're designing these sorts of things, right? Like how fast could a car go? And you want to account for the weather and different conditions, right? Different people driving above or below, above usually, not below, but above the speed limit, right? So when you're kind of designing, you want to think about various worst case scenarios. So this is kind of a simple example of, hey, if there is ice on the road, let's assume the friction is zero, can this car go around a circle, right, safely? All right, questions about that?
There's some confusion about the positive or negatives for the centripetal acceleration part and how it was in the negative x direction.
Oh yeah, so let's go back here, right? So hopefully you're kind of getting familiar with applying the F equals ma formulas, right? So x and y, right? So summing up forces, you're probably familiar with that. This side, the ma part of F equals ma, can be confusing, right? So one of the things to determine is, in each direction, is there acceleration? Sometimes you're told there's acceleration, sometimes you're told there isn't acceleration, right? But sometimes you have to determine, hey, is it reasonable to expect some acceleration? Well, the y's may be the easier one to deal with, because in the y direction you can say, yeah, I don't expect to see an acceleration in this direction, right? As the car goes around the ramp, I expect the car to be in contact with the road. It's not levitating, it's not bearing itself into the ramp, it's not moving, right, in this direction, it's not accelerating this direction. So F equals ma, ma is 0. In this case, the x direction, F equals ma, there is an ma, right? Because we know that this car is going around in a circle. And we talked about centripetal acceleration. If it's going around a circle, it has a centripetal acceleration that's that way, right? It's centripetal, center seeking, points to the center, right? All I'm saying is that the acceleration that points like this in this diagram, in the side view, is equivalent to that direction, right? Negative x, right? Because the center of the circle is that way in this view, okay? And why is it negative? Well, it points this way, positive x is that way, right? So it's the opposite of positive x, that's why I listed a negative number, right? When you know the direction of acceleration, right, you put that in to F equals ma. If you don't know, list it as a ma, because I don't know what the direction is. In this case, I know something about acceleration. I know where it is pointing. It's in the negative direction. That's the m part. This is a as v squared over r, right? Centripetal acceleration from what we talked about earlier. And hopefully that clears up why this is here. Maybe ask us more questions if that's not clear.
We had a question asking As the car moves along the x-axis, doesn't it go uphill and therefore move along the y-axis?
As the car goes along the x, say that one more time. Sorry.
They ask if as a car moves along the x-axis, doesn't it go uphill? I think they're thinking if the car moving along those x and y axes, or is it just staying in this scenario at least?
Yeah, so we're kind of freezing this at a moment and considering it at this moment what's going on, right? So we're not really following the car throughout the whole process. We're just saying, let's freeze time for a second, let's analyze the forces in this moment, right? And in this moment, that thing about the coordinate system is true as well. I'm just freezing the coordinate system at the center of the car. I'm not putting the coordinate system onto the car, right? Because if I stick the coordinate system with the car and the car is going around the circle, then the coordinate system itself is accelerating and it causes these problems I talked about, right? It creates fictitious forces and it makes it a little bit harder to deal with. So in this case, just to simplify, what I'm saying is the car's going around the ramp, I'm going to freeze a moment in time, and at that moment in time, I'm just going to center the coordinate system at the car. I'm not saying I'm attaching it to the car, and I'm analyzing the forces in that moment, and that's enough to get what I need for the angle, for instance, right, of this ramp. Okay, we'll stop here. Keep asking us questions. Come to drop-in hours, right? Make sure you're working on your homework. Don't put it off till the last minute. Not a good idea. We'll pick this up on Monday.